So here are some results from this paper. This is a first set of results. So what we have on this axis is the number of training examples, I believe in terms of number of words. So we go from 1,000 to 10,000 to 100,000 to 1,000,000 words. This is actually on a log scale, you'll notice. And on this axis we have the F-measure accuracy of the named entity recognizer. So this measure is actually a combination of precision and recall. It's actually, the F-measure is equal to 2 times the precision times the recall over the precision plus the recall. You can basically just think of this as a kind of averaging with the precision and recall, where 100 is perfect performance. 85, for example, means you have roughly 85% accuracy. So it's really just a way of taking these two numbers, precision and recall, and forming a single number measuring the accuracy. So let's see what we have on this curve. So firstly we have an HMM, which was basically the best model they had up to this point. And this was a serious model. This was an HMM model which they had developed over several years and was a very, very good named entity recognizer. Here in pink, you can see we have the model I just showed you, which is the log linear tagger in combination with the brown clusters. It's worth noting that without the clusters, the log linear tagger has very similar performance to the HMM. I haven't showed that on this slide, but for this task, the log linear model and the HMM had roughly comparable performance. So what you'll see here is there's a pretty substantial difference between these two curves. The cluster information really adds quite a bit in terms of accuracy. Over 5% here, over 5% here, that's at 10,000 words of training, I think, and so on and so on. Or if you think about it another way, if you want to achieve this level of performance, you would need this much data under the HMM, and you would need roughly this much data under the discriminative model, rather the cluster-based model. And notice that this is on a log scale, so this is a pretty substantial difference. So that in itself is quite an impressive result. The final result I'll show actually throws another very useful technique at this problem, and this is a problem called active learning. So in most of the methods that we've seen in this class, you are given a fixed set of training examples. You train a model from those examples and then you test on your test data. In active learning, you attempt to reduce the number of training examples you need by dynamically choosing which examples should be labeled, and you in particular choose to label the most useful examples at each stage. What that would typically mean is you would train your log linear tagger on a small number of examples, maybe 500. You would have a large pool of additional examples which you could send to an annotator for labeling, and you would choose to label the examples which are most difficult for the log linear tagger, maybe where the log linear tagger has most confusion by some measure or another. And so in this way you end up, rather than repeatedly labeling examples for which you already have a very good idea of what's going on, you choose examples which are more challenging and which essentially contain more information for the current learning algorithm. So that's active learning. It's the idea that you can dynamically select examples based on how informative they are. This is well known to give some pretty significant reductions in the amount of training data that's required. So here are some different curves. This is the baseline model. This is just a log linear tagger with no active learning and with no use of those word clusters that I showed you. If we use active learning, we get to this pink curve, and you can see again there's some fairly significant improvements. The yellow curve is the result with brown clusters. So again, you can see a good improvement over the method that doesn't use clusters. And finally, and most impressively, we have a result which makes use of both the brown clusters and also active learning. If we look at this, the performance really is rather remarkable. I can get over 90% performance with, sorry, that's not a very straight line, but with on the order of roughly 10,000 words of training data. And so if we look at this level of performance, we would have needed a few 100,000 words of training data under the old method. We would have been over here. So this combination of the brown clustering information and active learning has vastly reduced the amount of labeled data that we need. And as we saw in the motivation for this work, that is certainly a very useful thing in many contexts. So what I've spoken about here is results for named entity recognition. But this kind of technique can apply to many other problems. Another problem where brown clusters have been shown to be very useful is the parsing problem, where again we have severe problems with sparse data, and these brown clusters can really improve things. The final thing I'll say here is that note that the use of log linear models was critical in that it enabled us to use these representations, these brown clustering representations, in a really seamless and straightforward way. It would have been much more challenging to have used those representations within a hidden Markov model. So again, as I said before, a selling point of log linear models is the flexibility in terms of the representations they can use, and here we've used that flexibility to directly leverage information from brown clusters, which themselves are derived from very large quantities of unlabeled data, maybe tens or hundreds of millions of words of unlabeled data.